redistribute spectral weight somewhat, but the underlying features remain the same.
Can you say that the similarity comes from the infinite dimension?
In the calculation, yes. In the calculation, yes. Because we do not know what will happen in 3 dimensions. Nobody can do this calculation in finite dimension.
So there may be a possibility.
There is always the possibility. That's why I made a point to point out that this is an approximation when we are applying it to the 3-dimensional space. Right? But as you know, we always do this. I mean, 1 over n expansion for the all the F electron system, where n was considered to be large, n was 14, so it was fine. Then we found if you put in spin orbit splitting, n came down to 6. You put in crystal field splitting, n came down to 2. And still we did 1 over n expansion and it seems to work. So these are the problems, and we have to go to some limiting behaviors to get exact statements, because it is important to get exact statements. Okay, the next problem that I'm going to tackle, I think, say I'm going slower than I intended, but since it's not a graduate class where you have to finish a syllabus, I'll talk for 1 hour, and wherever I stop is all right. If I cannot cover everything I wanted to speak, instead of 3 systems that I promised to talk, maybe I'll talk about 2 systems. We'll see how we go, but it's better that I go slowly. I hope you agree with me, yeah? So the next problem that I'm going to discuss is lanthanum manganate doped with a divalent cation at the lanthanum site. Lanthanum is trivalent. Divalent cation, it could be calcium, strontium, barium, lead, etc. It has some very interesting properties. This is again a collaboration between my group in Bangalore, Professor Fujimori's group in Tokyo, Professor Tangel's group in Berlin, and some very recent result that I'm showing you from Professor Mobilio's group in Frascati. We had looked at this problem in the early days before much hullabaloo about these systems started in 95, and those works were done in the range of 91 to 93, and I'll show you some of these results. Now, what is interesting about this system? Lanthanum manganate itself is an A-type antiferromagnet. Don't worry what the A-type is. I mean, if you're interested, we can discuss, but that's not important for today's discussion. And it's an insulator, which is all nice and fine. There's no problem. If you dope strontium in place of lanthanum, what you're doing is to dope holes into the system. When you dope holes into the system, this antiferromagnet becomes ferromagnetic and becomes downstate metallic. There's also no problem with that. Most of the systems, like you take lanthanum cobaltate instead of lanthanum manganate, dope with strontium, lanthanum strontium cobaltate, becomes ferromagnetic and metallic. So that's very similar with other systems. But the problem becomes, when you look at the way it becomes metallic. For any given composition X, let's say 0.2, to find that at room temperature, the resistivity, there is a schematic resistivity plot, appears as an insulator. That is, as you lower the temperature, the resistivity is increasing. And it is exponentially increasing. Then comes a certain temperature, Tc, which is also the Curie temperature, the resistivity turns over and becomes metal. So it has an insulator to metal transition at finite hole doping at the magnetic transition, which already makes the system very interesting, very rich electronic and magnetic phases. And it looks like this magnetism and electronic transport is intimately connected. It needs this ferromagnetic transition for the insulator to become metal. And if you hold the system at this temperature, when it has the highest resistivity, and at a fixed temperature, apply magnetic field, the resistivity drops down drastically. So it has a negative magnetoresistance. And this negative magnetoresistance is very large. That's why it's called giant or colossal magnetoresistance. And this has created a lot